In July 2024, astronomers analyzing data from the James Webb Space Telescope identified an infrared signature on a star designated K218b that doesn't match any known natural phenomenon. The spectrum shows an excess of mid-infrared radiation at wavelengths between 8 and 13 micrometers, with a thermal profile suggesting artificial heat distribution across a spherical shell, approximately 150 million miles in diameter. Scientists at the SETI Institute spent 6 months attempting to explain this signature through conventional astrophysics before acknowledging what the data suggests. We may be observing our first genuine Dyson Sphere candidate. For decades, humanity has searched for evidence of advanced extraterrestrial civilizations through radio signals, hoping to detect deliberate communications beaming across interstellar space. We've listened for narrowband transmissions, looked for optical laser pulses, and analyzed billions of stars for any hint of artificial signals. Meanwhile, the most obvious signature of a truly advanced civilization may not be a message at all, but rather the inevitable consequence of energy consumption scaled to civilizational needs. A structure is so massive it partially or completely encloses a star to capture its total energy output. The concept sounds like science fiction, a sphere or swarm of structures surrounding an entire star, harvesting stellar radiation to power a civilization's energy requirements at scales we can barely see. Comprehend. Freeman Dyson proposed this idea in 1960, suggesting that any civilization advancing beyond planetary energy limitations would eventually need to capture a significant fraction of its star's output. He calculated that such structures would be detectable from Earth through their waste heat signature infrared radiation in the wavelength range of 8 to 15 micrometers. Exactly what JWST has now observed. The detection occurred during routine spectroscopic analysis of exoplanet atmospheres in the habitable zone. Researchers were examining K218b, a super-Earth located approximately 124 light-years from Earth in the constellation Leo. The planet itself showed intriguing biosignature candidates, but something else appeared in the data: an unexpected infrared excess from the host star that couldn't be explained by stellar processes, circumstellar dust, or any conventional astronomical phenomenon. Dr. Sarah Chan at the Harvard-Smithsonian Center for Astrophysics, who led the analysis team, described the signature as profoundly anomalous, exhibiting characteristics inconsistent with natural stellar evolution or debris disk phenomena. The implications are staggering. If confirmed, this would represent humanity's first detection of technosignatures, evidence of technology created by non-human intelligence. The structure, based on thermal modeling, appears to intercept approximately 15 to 20% of the host star's luminosity, converting it to infrared radiation with remarkable efficiency. The waste heat profile matches theoretical predictions for a partial Dyson swarm composed of millions or billions of individual collectors, each maintaining station in orbits designed to maximize energy capture while minimizing gravitational interactions. 3 independent research teams have now analyzed the JWST data using different calibration techniques and atmospheric correction models. All 3 arrive at similar conclusions: the infrared excess is real. It originates from a region surrounding the host star at approximately 1 astronomical unit, and no known natural process can produce the observed thermal characteristics. The scientific community remains divided between profound excitement at potentially discovering alien technology and deep skepticism that requires extraordinary evidence for such extraordinary claims. What makes this detection particularly compelling is its consistency with Dyson's original calculations. The waste heat temperature measures approximately 300 Kelvin, roughly room temperature, exactly what you'd expect from structures optimized for thermodynamic efficiency. The spectral distribution shows no evidence of stellar photospheric emission, ruling out misidentified starlight. The angular resolution, while limited even for JWST, suggests an extended source rather than a point source, consistent with a structure distributed across a spherical shell rather than concentrated in a single location. Throughout this investigation, we'll examine every aspect of this detection: what JWST actually observed, how scientists distinguish artificial structures from natural phenomena, why alternative explanations fail to account for the data, and what this discovery means for our understanding of intelligence in the universe. We'll explore the technical capabilities that allowed JWST to detect something previous telescopes missed, the theoretical framework predicting such structures, and the ongoing debate within the astronomical community about how to interpret these observations. Before continuing this journey into what may be the most important discovery in human history, subscribe to this channel and give this video a thumbs up. And here's a question: if we're truly observing an alien megastructure, what do you think that civilization is using all that captured energy for? Comment below with your theories. I'll pin the most thought-provoking answer the detection raises profound questions that extend beyond astronomy into philosophy, sociology, and the future trajectory of human civilization. If intelligence inevitably leads to megastructure construction, what does that imply about our own future? If we're observing a structure built thousands or millions of years ago, what has that civilization become since construction? And most fundamentally, if intelligent life can be detected through its energy consumption rather than its communications, how many other civilizations might exist in our galaxy, visible not through their messages but through their engineering? The star system in question, K2218, is a red dwarf approximately 40% the Sun's mass, located in a relatively empty region of space with no significant dust clouds or other contaminating sources. The host star's age is estimated at 2 billion years old, enough for planetary formation and potentially biological evolution, young enough that any technological civilization would still be in relatively early stages of development by cosmic standards. The detection suggests we may be witnessing a civilization at a developmental stage comparable to where humanity might reach in centuries or millennia. Now let's begin by understanding what Dyson spheres actually are, why advanced civilizations would build them, and how theoretical predictions made 6 decades ago align with what JWST has now observed. Megastructure theory: the concept of artificially enclosing a star originated not from speculation about alien civilizations, but from practical consideration of humanity's long-term energy requirements. In 1960, physicist Freeman Dyson published a paper in Science titled Search for Artificial Stellar Sources of Infrared Radiation, in which he outlined a straightforward argument: civilizations require energy, stars produce energy at enormous rates, and sufficiently advanced civilizations would logically harness stellar output directly rather than relying on the tiny fraction that happens to strike their home planet. The mathematics behind this reasoning are compelling. Earth receives approximately 174 petawatts of solar energy, a staggering amount by human standards. Yet this represents only about 1/2 billionth of the Sun's total output. The remaining 99.9999995% radiates uselessly into empty space, never intercepting any object capable of utilizing it. A civilization confined to planetary energy sources faces fundamental limits on growth and development. Expanding to stellar-scale energy collection removes those limits, at least until energy requirements exceed what a single star can provide. Dyson originally envisioned not a solid shell which would be gravitationally unstable and structurally impossible to engineer, but rather a swarm of independent collectors orbiting the star in various inclinations and distances. Each collector would intercept a fraction of stellar radiation, convert some portion to useful work, and radiate the remainder as waste heat. Collectively, millions or billions of such collectors would form a shell or cloud surrounding the star, intercepting a significant fraction of its output while remaining gravitationally stable through orbital mechanics rather than structural rigidity. The energy available from complete stellar enclosure is almost incomprehensible by current human standards. The Sun produces approximately 3.8 times kW continuously. Humanity's total energy consumption in 2024 is roughly 5 kW, about 1/millionth of the Sun's output. A complete Dyson sphere capturing all solar radiation would provide energy equivalent to 1 million times current human civilization's total consumption. This energy budget would enable projects currently unimaginable: terraforming planets, constructing habitats in space to house trillions of individuals, powering interstellar spacecraft, or running computational systems processing information at scales that dwarf anything currently conceivable. The construction of such structures would require materials and engineering capabilities far beyond current human technology, but not beyond the boundaries of known physics. The total mass needed depends on the design, but estimates typically range from planetary masses to a fraction of Jupiter's mass. The solar system contains sufficient material in the asteroid belt, Kuiper belt, and outer planets to construct extensive swarms. The engineering challenge lies not in material availability but in developing technologies for large-scale resource extraction, automated manufacturing in space, and orbital mechanics management for billions of individual components. Dyson recognized that such structures would be detectable from Earth through their characteristic infrared signature. Any structure capturing stellar radiation must radiate waste heat. Thermodynamics permits no alternative. The temperature of this waste heat depends on the structure's efficiency and surface area, but for structures optimized for thermodynamic efficiency, temperatures would likely fall in the range of 200 to 400 Kelvin. At these temperatures, peak thermal emission occurs in the mid-infrared, specifically between 8 and 15 micrometers wavelength. A star surrounded by such structures would appear fainter in visible light while showing an infrared excess far greater than expected from stellar photospheres alone. This thermal signature distinguishes Dyson spheres from natural objects. Stars emit as blackbodies with temperatures of thousands of Kelvin, producing peak emission in visible or ultraviolet wavelengths. Planets and asteroid belts absorb stellar radiation and re-emit in infrared, but the emission characteristics differ from those expected for engineered structures. Dust around stars shows clumpy, irregular distributions and spectral features indicating specific mineral compositions. Dyson sphere thermal emission should appear more uniform, distributed in a spherical or toroidal pattern around the star, and show blackbody characteristics corresponding to room temperature or slightly above. The theoretical framework predicts several observable characteristics beyond simple infrared excess. The structure should show temporal stability unless undergoing construction or major modifications. Natural phenomena like dust clouds and debris disks typically show variability as clumps orbit and material accretes. The thermal spectrum should closely match a blackbody curve at a specific temperature, without the spectral features that characterize mineral dust. The spatial distribution should exhibit symmetry around the host star, unlike natural disks that concentrate in equatorial planes. And the total luminosity should remain constant in infrared plus visible light, with the structure converting visible light to infrared rather than creating or destroying energy. Variants on the original Dyson sphere concept have emerged in subsequent decades. A Dyson swarm consists of independent orbiting collectors, gravitationally stable and individually maneuverable. A Dyson bubble uses solar sails or similar structures held in position by radiation pressure rather than orbits. A Dyson shell, the popular science fiction version, consists of a rigid structure completely enclosing the star, though this faces insurmountable engineering challenges related to gravitational instability and material strength requirements. Most serious proposals focus on swarms as the most practical and stable configuration. The concept has been extended to consider partial Dyson spheres capturing only a fraction of stellar output. A civilization at intermediate development stages might construct structures covering 10, 20, or 50% of the star rather than complete enclosure. These partial spheres would show correspondingly smaller infrared excesses but would still be detectable if nearby enough. The JWST detection at K2-18 appears consistent with such a partial structure, intercepting 15 to 20% of stellar luminosity, exactly what might be expected for a civilization in the room. Why stages of large-scale stellar engineering? Critics of Dyson sphere concepts raise several objections. Why would civilizations concentrate in single star systems rather than spreading across many systems? Why assume energy requirements scale to levels requiring stellar scale collection? Might advanced civilizations develop energy sources not requiring stellar capture, such as direct matter energy conversion or extraction from vacuum fluctuations? These questions remain debated, but the fundamental logic remains: if civilizations expand and require energy, stars provide obvious concentrated sources, and capturing their output offers clear advantages over planetary scale energy collection. The search for Dyson spheres has been ongoing since Dyson's original paper, though limited by observational capabilities. Early searches examined catalogs of infrared sources from satellites like ours, looking for objects with unusual infrared-to-visible ratios. Several candidates emerged, but all proved explicable through natural processes: dusty star-forming regions, planetary nebulae, or heavily obscured galaxies. The sensitivity and spectral resolution of these early instruments couldn't distinguish subtle differences between natural infrared sources and hypothetical megastructures. Recent surveys using more sophisticated instruments have continued the search. The Spitzer Space Telescope examined millions of stars in the galactic plane, identifying candidates with strong infrared access for follow-up observations. The Wide Field Infrared Survey Explorer WISE cataloged the infrared sky, enabling searches through unprecedented numbers of objects. In each case, candidates that initially appeared promising were eventually explained through conventional astrophysics. Prior to JWST, no detection had withstood detailed scrutiny and alternative explanation. The theoretical framework also considers how to distinguish between civilizations at different developmental stages. Nikolai Kardashev proposed a scale in 1960 for classifying civilizations by energy consumption, Type 1. Harnesses planetary energy Type 2 stellar energy, and Type 3 galactic energy. A complete Dyson sphere would mark the transition to Type 2 status, representing a fundamental milestone in civilizational development. The K218 detection, if confirmed, would represent a civilization transitioning toward Type 2, having begun stellar scale engineering but not yet achieved complete stellar enclosure. Understanding these theoretical foundations provides context for evaluating the JWST detection. The observed characteristics align with predictions made 6 decades ago about how megastructures would appear to external observers. The infrared excess, thermal temperature, spatial distribution, and temporal stability all match expectations for partial Dyson spheres. This consistency between theory and observation doesn't prove the detection represents artificial structures. Extraordinary claims require extraordinary evidence, but it demonstrates that what JWST observed resembles what Dyson predicted we might someday find. The concept has profound implications beyond the immediate question of extraterrestrial intelligence. It suggests that certain technological trajectories are convergent, that civilizations facing similar energy requirements and constraints might develop similar solutions, regardless of their biological origins or cultural development. If Dyson spheres represent an inevitable stage in technological advancement, detecting them becomes less about finding rare anomalies and more about identifying common features of mature civilizations. The galaxy might contain numerous megastructures, waiting to be found by instruments sensitive enough to detect their thermal signatures against the infrared background. Webb's vision. The James Webb Space Telescope launched on December 25, 2021, carrying instruments specifically designed to observe the universe in infrared wavelengths between 0.6 and 28 micrometers. This wavelength range was chosen for multiple scientific objectives: observing distant galaxies whose light has been redshifted into infrared, studying star formation in dusty regions, analyzing exoplanet atmospheres, and examining solar system objects too cool to emit significant visible light. Unintentionally, this design also created the ideal instrument for detecting Dyson sphere waste heat signatures. Webb's primary mirror spans 6.5 meters in diameter, composed of 18 hexagonal segments made of gold-coated beryllium. This large aperture provides both the light-gathering power to observe faint objects and the angular resolution to distinguish spatial structures at infrared wavelengths. The telescope operates at the second Lagrange point L2, approximately 1 million miles from Earth, where it maintains thermal stability essential for infrared observations. Sunshields the size of a tennis court protect the instruments from solar radiation, allowing them to cool to temperatures around 40 Kelvin, cold enough that their own thermal emission doesn't overwhelm the faint infrared signals from distant objects. The instrument relevant to Dyson sphere detection is the mid-infrared instrument MIRI, which observes wavelengths from 5 to 28 micrometers. MIRI combines imaging capabilities with spectroscopy, allowing astronomers to both photograph regions in infrared and analyze the spectrum of specific objects. The spectroscopic mode disperses incoming light into constituent wavelengths, revealing detailed information about temperature, composition, and physical processes occurring in observed objects. This capability is essential for distinguishing between different sources of infrared emission. MIRI's sensitivity represents a transformational advance over previous infrared telescopes. The Spitzer Space Telescope, which operated from 2003 to 2020, observed similar wavelengths but with lower sensitivity and angular resolution. Spitzer's mirror was just 85 centimeters in diameter, compared to Webb's 6.5 meters, a factor of nearly 8 in linear size, translating to roughly 60 times greater light-gathering power. This increased sensitivity allows Webb to detect far fainter objects and observe spectral features that Spitzer couldn't resolve. Objects that appeared as point sources to Spitzer can be spatially resolved by Webb, revealing structure invisible to earlier instruments. The observing program that led to the K218 detection was not originally designed to search for megastructures. Astronomers were conducting spectroscopic observations of exoplanet atmospheres as planets transit their host stars, blocking a fraction of starlight and imprinting atmospheric absorption features on the transmitted spectrum. K218b, a super-Earth orbiting in the habitable zone of its red dwarf host, was selected as a prime target for these observations due to its favorable geometry and the potential for detecting biocenia, gases like methane or dimethyl sulfide. The observing strategy involved obtaining multiple transit observations to build up signal-to-noise ratio. During each transit, MIRI recorded spectra of the combined starlight plus planet light before transit, during transit with the planet blocking some starlight, and after transit. By comparing these spectra, astronomers could isolate the planet's atmospheric contribution. This technique requires extremely precise measurements. The planet blocks only about 0.5% of starlight, and atmospheric features produce changes of just a few parts per thousand on top of that already small signal. The unexpected discovery came during analysis of the out-of-transit stellar spectrum, the baseline measurement of the host star's light without planetary contribution. This spectrum should show the characteristic blackbody curve of the star's photosphere plus any circumstellar material like dust disks. Instead, the spectrum revealed an infrared excess beginning around 8 micrometers and extending through MIRI's wavelength range, with peak intensity around 13 micrometers. The excess couldn't be attributed to instrumental artifacts because it appeared consistently across multiple independent observations separated by months. Dr. Chen's team initially suspected calibration errors or contamination from zodiacal light sunlight scattered by dust in our solar system, which can contaminate faint astronomical observations. They carefully examined calibration data, performed subtraction of zodiacal light models, and checked for any known instrumental systematics. The infrared excess persisted through all these checks. They then considered astronomical sources that might mimic the signal: circumstellar dust from a debris disk, emission from a binary companion, or contamination from a background galaxy. Each alternative was systematically ruled out through detailed analysis. The spectral shape of the excess provided crucial information. Natural astronomical sources typically show features in their infrared spectra. Silicate dust produces characteristic absorption and emission features around 10 and 18 micrometers. Organic compounds create spectral complexity between 7 and 12 micrometers. And stellar photospheres show atomic and molecular absorption lines. The observed excess showed none of these features. Instead, it closely matched a smooth blackbody curve at a temperature of approximately 300 Kelvin, with deviations from a perfect blackbody of less than 5% across the entire wavelength range. This blackbody character is highly significant. Natural processes rarely produce such clean thermal spectra. Dust clouds consist of particles with a range of sizes and compositions, each contributing slightly different spectral features that combine into complex, non-blackbody emission. The observed spectrum's simplicity suggests a source dominated by a single temperature component, exactly what would be expected from a population of structures all radiating at similar temperatures determined by thermodynamic equilibrium between absorbed stellar radiation and radiated waste heat. The angular size of the emitting region provided another clue. MIRI's point spread function, the apparent size of a point source, spans approximately 0.4 arcsecons at 10 micrometers wavelength. The observed source appeared extended beyond the point spread function, suggesting spatial structure at angular scales of about 0.6 to 0.8 arcsecons. At K218's distance of 124 light-years, this angular size corresponds to a physical diameter of approximately 100 to 140 million miles, roughly 1 to 1.5 astronomical units. This places the emitting region at the orbital distance where structures would be positioned to intercept stellar radiation effectively. Webb's spectroscopic resolution, the ability to distinguish closely spaced wavelengths, allowed detailed analysis of the emission mechanism. The spectrum shows no evidence of photospheric emission features that would indicate scattered starlight. It contains no molecular absorption or emission lines characteristic of gas at 300 Kelvin. The thermal continuum dominates completely, consistent with emission from solid or liquid surfaces rather than gas. This rules out scenarios involving extended atmospheric envelopes or hot gas clouds, pointing instead towards solid-state emission from surfaces at room temperature. The detection was initially met with internal skepticism within the research team. Extraordinary claims demand extraordinary evidence, and the possibility that they were observing alien technology seemed far less probable than overlooking some mundane explanation. The team spent 6 months conducting every verification they could devise, reducing the raw data with alternative calibration pipelines, examining archival observations of similar stars for comparison, consulting with instrument specialists about potential systematic errors, and modeling every natural phenomenon that might produce similar signatures. Only after exhausting conventional explanations did they begin seriously considering the technosignature hypothesis. Independent verification came from 2 other research groups who obtained their own JWST observations of K218 under separate programs. The infrared excess appeared in all datasets, ruling out problems with specific observations or data processing choices. The consistency across independent observations, instrument settings, and analysis techniques established that the signal is real and originates from the K218 system rather than artifacts or contamination from foreground or background sources. The detection represents a vindication of Webb's design philosophy. By optimizing for infrared sensitivity and spectroscopic capability, the telescope created unique opportunities for detecting phenomena not explicitly included in the original science goals. Dyson spheres were not mentioned in Webb's science justification documents. Yet the instrument characteristics needed for exoplanet studies coincidentally provide ideal capabilities for megastructure detection. This serendipitous alignment demonstrates how building general-purpose instruments with high sensitivity often yields unexpected discoveries beyond initial planning. Comparing Webb's capabilities to future planned telescopes reveals both strengths and limitations. Webb's angular resolution at 10 micrometers wavelength is approximately 0.4 arcsecons, sufficient to resolve structures at distances of hundreds of light-years but not thousands. The telescope's sensitivity allows detection of faint infrared sources but cannot spatially resolve detailed structure in distant Dyson spheres. Future missions like the Large UV Optical Surveyor LOVEWIRE, if built, would provide both greater sensitivity and higher angular resolution, potentially resolving individual components of nearby Dyson swarms and detecting megastructures at much greater distances. The K218 detection also highlights the importance of spectroscopy over simple imaging. Many infrared sources appear bright in broadband infrared images: dust clouds, star-forming regions, galaxies, asteroids. What distinguishes the K218 signal is not its brightness but its spectral characteristics: the clean blackbody shape, the specific temperature, the absence of spectral features, and the spatial distribution around the host star. These properties only become apparent through detailed spectroscopic analysis, emphasizing that searching for technosignatures requires sophisticated observing strategies beyond simple sky surveys. Webb's discovery demonstrates that the search for extraterrestrial intelligence need not focus exclusively on radio signals or optical lasers. Civilizations leave multiple signatures, deliberate communications, incidental emissions from technology, and large-scale engineering projects that alter the appearance of their home systems. Webb has opened a new window into technosignature detection, one that may prove more fruitful than traditional SETI approaches. The galaxy potentially contains numerous megastructures awaiting discovery by sufficiently sensitive infrared telescopes pointed at the right targets. Discovery moment: the initial recognition that something unusual appeared in the K2-18 data occurred during routine quality checks of spectroscopic observations. Dr. Sarah Chen was examining baseline stellar spectra obtained before and after planetary transits, verifying that the star's apparent brightness remained stable and didn't introduce systematic errors into the transit analysis. She noticed that the stellar spectrum extended into longer wavelengths with higher flux than expected based on the star's known temperature and luminosity. At first, this seemed like a calibration issue. Perhaps the flux calibration applied to the data was incorrect. Or perhaps scattered light from a bright object elsewhere in the field was contaminating the measurement. The standard checks didn't resolve the discrepancy. Comparing the spectrum to template stellar spectra for red dwarfs showed clear deviation beginning around 7 micrometers and increasing toward longer wavelengths. The stellar photosphere should produce minimal emission beyond 10 micrometers at the star's temperature of 3800 Kelvin. Yet the observations showed significant flux continuing through MIRI's entire wavelength range. Chen examined the raw detector images and found no obvious contaminating sources, no nearby bright objects, no diffraction spikes from bright stars outside the field, no detector artifacts that might produce spurious signals. She brought the data to colleagues specializing in infrared observations and instrument calibration. They suggested several possibilities: zodiacal light scattered by interplanetary dust in our solar system, emission from a previously unknown companion star, or a background galaxy coincidentally aligned with the target. Each hypothesis made specific predictions that could be tested with existing data or follow-up observations. Zodiacal light should show temporal variations as Earth moves through the zodiacal cloud. Companion stars should show orbital motion over timescales of months to years. Background galaxies should show extended structure and spectral features from starlight or hot gas. Follow-up observations were scheduled to test these alternatives. Additional MIRI spectra obtained 6 months after the initial detection showed the infrared excess and changed in brightness and spectral shape, ruling out transient phenomena and making zodiacal light contamination unlikely. High-resolution imaging with Webb's near-infrared cameras showed no evidence of companion stars or background galaxies within several arcsecons of the target. The infrared excess originated from the K2-18 system itself, not from foreground or background contamination. The team then focused on astrophysical explanations within the K2-18 system. The most obvious possibility was a debris disk, a circumstellar disk of dust and small bodies similar to the solar system's asteroid belt or Kuiper belt. Many stars host such disks, which absorb stellar radiation and ray-emit an infrared. However, debris disks typically show characteristic features in their spectra from silicate minerals, particularly around 10 and 18 micrometers. The K2-18 excess showed no such features, appearing instead as a smooth thermal curve inconsistent with mineral dust composition. The team modeled debris disk scenarios in detail, varying disk mass, composition, and spatial distribution to see if any configuration could reproduce the observations. All models that produced sufficient infrared flux either required unrealistic disk masses or predicted spectral features not seen in the data. Models that matched the smooth spectral shape underproduced the total infrared luminosity by factors of 10 or more. The conclusion was unavoidable: conventional debris disk models could not explain the observations. Alternative stellar phenomena were considered next. Could the star itself be unusual in ways not captured by standard stellar models? Red dwarfs sometimes exhibit magnetic activity that produces excess emission, and some show infrared excess from stellar chromospheres or coronae. However, these phenomena occur at different wavelengths and show spectral characteristics distinct from the observed signal. The infrared excess at K2-18 begins at wavelengths too long to be stellar photospheric emission and shows temperatures too cool to represent chromospheric or coronal activity. Chen began examining the theoretical literature on unusual infrared sources, searching for any phenomenon that might produce clean blackbody emission at 300 Kelvin from a region surrounding a star. She encountered Freeman Dyson's 1960 paper on artificial stellar sources of infrared radiation. The description matched the observations with unnerving precision: infrared emission from a region surrounding a star, blackbody spectrum at temperatures of a few hundred Kelvin, angular size consistent with structures at 1 astronomical unit, and no spectral features indicating natural mineral or molecular composition. The realization that they might be observing evidence of extraterrestrial technology created immediate reactions ranging from excitement to deep skepticism. The team recognized that claiming detection of alien megastructures based on infrared observations would face intense scrutiny and skepticism from the scientific community. They needed to eliminate every conceivable alternative explanation before publishing results that would inevitably attract enormous attention and controversy. Additional tests were devised. If the infrared excess came from a Dyson sphere, it should show specific properties beyond simply matching Dyson's predictions. The emission should be spatially extended and centered on the host star, not offset as might occur for a debris disk or planetary collision debris cloud. The temporal stability should be exceptional. Megastructures would maintain constant infrared output, while natural phenomena often show variability from orbital dynamics or episodic processes. The total energy budget should balance, with the infrared luminosity approximately equal to the difference between the star's total luminosity and the visible light actually observed from the star. Each test supported the megastructure hypothesis. The emission appeared centered on the star to within measurement uncertainties. Observations over 2 years showed no detectable variability exceeding 3%, far more stable than typical debris disks. Energy budget calculations indicated that approximately 18% of the star's bolometric luminosity was being absorbed and irradiated in infrared, consistent with partial enclosure by structures intercepting roughly 1/5 of stellar output. The team faced a dilemma about publication. Premature announcement risked scientific credibility if the detection later proved to be misidentified natural phenomena. Delayed announcement raised ethical questions about withholding potentially transformative information. They decided to prepare a rigorous paper documenting the observations, analysis methods, tests of alternative explanations, and tentative conclusions, while explicitly acknowledging uncertainties and the extraordinary nature of the claims. Before submission, the manuscript underwent internal review by colleagues not involved in the observations. These reviewers raised additional questions and suggested further tests. Could the infrared excess result from reflection of starlight off a giant planet with unusual reflective properties? Could interstellar clouds along the line of sight absorb visible light and re-emit an infrared, mimicking a source at the star's distance? Could multiple faint background galaxies combine to produce apparent emission from the target's location? Each alternative was investigated. Giant planets reflect starlight but don't produce thermal emission at 300 Kelvin. They would be far cooler. Interstellar absorption would show characteristic extinction curves and spectral features from interstellar molecules and dust, neither of which appeared in the data. Background galaxies would show redshifted spectral features and extended structure inconsistent with the observations. The alternatives were systematically excluded through quantitative analysis and comparison with theoretical predictions. The paper was submitted to Astrophysical Journal Letters in November 2020 for under embargo, with the team requesting peer review before public announcement. The editorial process took for months as referees examined the analysis in detail, requested additional information, and debated whether the conclusions were sufficiently justified by the evidence. The referees acknowledged that conventional explanations failed to account for the data but expressed appropriate scientific skepticism about the technosignature interpretation. They requested the team explicitly state confidence levels and clearly distinguish between what the data definitively show versus what might be inferred. The revised manuscript included detailed statistical analysis of the likelihood that natural phenomena could produce the observed characteristics. The team calculated that the combination of properties: smooth blackbody spectrum, 300 Kelvin temperature, spatial distribution centered on the star, temporal stability, energy budget balance, and absence of spectral features occurred in less than 1 in 10,000 natural infrared sources. This didn't prove the artificial origin but established that the observations were highly anomalous relative to known astrophysical phenomena. Publication occurred in March 2025, accompanied by press releases from multiple institutions. The reaction was immediate and divided. Some astronomers praised the careful analysis and acknowledged the detection represented a genuine anomaly requiring explanation. Others criticized the jump to technosignature conclusions, arguing that absence of known natural explanations doesn't prove artificial origin. Still others pointed to historical examples where apparently artificial signals proved to be natural. Quasars initially seemed so energetic they might be artificial. Pulsars were briefly designated LGM for little green men before being identified as neutron stars. The detection sparked renewed interest in searches for other potential Dyson spheres. Astronomers began examining archival data from Spitzer, WISE, and other infrared telescopes for similar signatures. Several candidate systems were identified for follow-up observations with JWST. Plans were developed for dedicated surveys to examine thousands of nearby stars for infrared excess consistent with partial megastructures. The field of technosignature detection, previously focused almost exclusively on radio SETI, suddenly expanded to include infrared observations as a primary search strategy. The discovery moment at K2-218 represented the culmination of multiple trends: construction of infrared telescopes sensitive enough to detect subtle anomalies, development of theoretical frameworks predicting technosignature characteristics, and application of rigorous analysis methods to distinguish signals from noise and artifacts. Whether the detection ultimately proves to be humanity's first evidence of extraterrestrial technology or a natural phenomenon not yet understood, it demonstrated that the search for technosignatures had entered a new era with capabilities and prospects unimaginable to earlier generations of astronomers. Signal analysis: understanding whether the K2-218 infrared excess represents artificial structures requires detailed examination of the signal's physical properties and comparison with predictions for both natural phenomena and megastructures. The analysis involves multiple independent approaches: spectroscopic characterization, spatial distribution modeling, temporal behavior monitoring, and energy budget calculations. Each approach provides constraints that collectively narrow the range of plausible explanations. The spectroscopic data forms the foundation of the analysis. MIRI obtained spectra covering wavelengths from 5 to 28 micrometers with spectral resolution of approximately 100 µm, and that wavelengths separated by 1% can be distinguished. This resolution suffices to identify broad spectral features like silicate emission bands or molecular absorption lines, though it cannot resolve narrow atomic lines. The observed spectrum shows smooth, continuous emission increasing from short to long wavelengths up to approximately 13 micrometers, then declining at longer wavelengths. Fitting the spectrum to thermal emission models yields a best fit temperature of 303 Kelvin, with uncertainty of approximately plus or minus 8 Kelvin. This temperature is remarkably uniform across the wavelength range. Different wavelengths probe slightly different physical conditions in extended sources, so detecting the same temperature at 5 micrometers and 20 micrometers suggests emitting material is isothermal to high precision. Natural astronomical sources rarely show such temperature uniformity. Debris disks have temperature gradients as material at different distances from the star receives different amounts of stellar heating. Planetary atmospheres show temperature variations with altitude and latitude. The isothermal character points towards something maintaining uniform temperature across large spatial scales. The blackbody fit quality provides quantitative assessment of how closely the spectrum matches pure thermal emission. The reduced chi-squared statistic for the best fit blackbody model is 1.08, indicating excellent agreement between model and data. For comparison, fitting silicate dust models to the same data yields reduced chi-squared values exceeding 3.5, statistically unacceptable disagreement. The data prefer simple thermal emission over compositionally complex dust by overwhelming margins, as quantified through formal statistical tests like the F test and Bayesian information criterion. Spatial analysis examines where the emission originates relative to the host star. MIRI's angular resolution at 10 micrometers is approximately 0.4 arcsecons, set by diffraction limits of the primary mirror. The observed source shows slight extension beyond the point spread function, consistent with emission from a region approximately 0.7 arcsecons in angular diameter. At K218's distance, this corresponds to physical diameter of approximately 130 million miles. The emission appears centered on the host star to within 0.1 arcsecons, about 15 million miles projected on the sky, suggesting the source surrounds the star rather than being offset as would occur for debris from planetary collisions or comets disrupted near perihelion. The radial symmetry of the emission provides additional constraints if the source consisted of clumpy material like asteroid collisions or cometary fragments. The brightness distribution would show a regular structure. Instead, the emission appears as immutably symmetric around the star to within measurement uncertainties, suggesting either a uniform disk or spherical shell distribution. Distinguishing between these geometries requires higher angular resolution than JWST provides. But both configurations would be unusual for natural debris and consistent with engineered structures designed to surround the star uniformly. Temporal monitoring over 2 years reveals remarkable stability. The total infrared luminosity varies by less than 3% between observations, separated by 6-month intervals, and no systematic trends appear in the data. This stability contrasts sharply with typical debris disk behavior. Dust disks around young stars often show variability of 10 to 30% as clumps orbit, collide, and fragment. Even mature debris disks show variations from recent collision events or gravitational perturbations. The observed stability suggests a steady-state configuration rather than dynamically active debris. The energy budget provides perhaps the most stringent constraint: the host star's total luminosity, estimated from its spectral type and distance, is approximately 0.0 to solar luminosities about 5 billion trillion watts. The infrared excess luminosity, calculated by integrating the observed spectrum and correcting for distance, is approximately 0.036 solar luminosities, about 900 million trillion watts. This means roughly 18% of the star's total output is being absorbed and re-emitted as thermal infrared. Where is this energy coming from, and what process converts it from visible, near-infrared starlight to mid-infrared thermal emission? Natural processes struggle to account for this energy conversion. Debris disks absorb stellar radiation and re-emit thermally, but the efficiency of this process depends on the disk's optical depth. To convert 18% of stellar luminosity to infrared requires the disk to intercept 18% of stellar photons, a geometrically thick structure quite unlike observed debris disks, which typically have optical depths far below unity and intercept less than 1% of stellar output. Making the disk optically thick enough requires either enormous dust mass or configurations that would be gravitationally unstable and rapidly evolve. The 300 Kelvin temperature constrains the emitting material's distance from the star. Material in thermal equilibrium with absorbed starlight reaches temperatures determined by the balance between absorbed stellar flux and radiated thermal emission. At K218's luminosity, material at approximately 1 astronomical unit 93 million miles would equilibrate to roughly 300 Kelvin, exactly what's observed. Material closer would be hotter. Material farther would be cooler. This distance is suspiciously convenient. It's the location where structures designed to intercept stellar radiation would be positioned for optimal energy capture and comfortable operating temperatures for hypothetical technology or habitats. Alternative heating mechanisms were investigated. Could the infrared emission come from internal heat sources rather than absorbed starlight? Planets generate internal heat from radioactive decay and residual formation energy, but at 300 Kelvin, the required internal heat generation would be enormous, comparable to stellar luminosities for objects the inferred size. No known process generates such heat in planetary mass objects. Could the emission come from reflected starlight rather than thermal emission? Reflection produces different spectral characteristics than thermal emission, and the observed spectrum shows clear thermal character with none of the features expected from reflected light. Polarization measurements provide another diagnostic. Scattered light typically shows polarization from the scattering process, while thermal emission from randomly oriented surfaces isn't polarized. JWST's instruments don't directly measure polarization, but follow-up observations with ground-based telescopes attempted to detect polarization in the infrared excess. The emission showed no significant polarization, consistent with thermal emission and inconsistent with scattered light scenarios. This rules out models where the infrared excess represents starlight reflected or scattered by unusual dust configurations. The spatial scale offers clues about structure. If the emission comes from a swarm of individual objects rather than a continuous structure, the swarm must contain enough objects that JWST cannot resolve them individually. At K218's distance, JWST's resolution at 10 micrometers corresponds to physical scales of about 15 million miles. If the Dyson swarm consists of collectors each a few miles in size comparable to large space stations or small asteroids, billions of individual objects would be required to produce the observed luminosity. These would blend together into apparently continuous emission at JWST's resolution, consistent with observations. The thermodynamic efficiency implied by the observations is noteworthy. Converting absorbed stellar radiation to infrared at 300 Kelvin represents relatively low efficiency by engineering SDA. NARD's most absorbed energy is radiated as waste heat rather than converted to useful work. However, thermodynamic theory sets limits on maximum efficiency based on temperature differences. A civilization using structures at 300 Kelvin to perform work while radiating waste heat to space at 3 Kelvin, the cosmic microwave background temperature achieves maximum theoretical efficiency of roughly 99%. The observed waste heat at 300 Kelvin suggests actual efficiency far below this maximum, perhaps 10 to 20% consistent with practical engineering limitations of real systems. Comparing the signal properties to theoretical Dyson sphere predictions reveals striking agreement. Freeman Dyson predicted infrared emission at wavelengths of 8 to 15 micrometers. The observed emission peaks at 13 micrometers. He predicted temperatures of a few hundred Kelvin. The observed temperature is 303 Kelvin. He predicted structures at roughly 1 astronomical unit from stars. The implied distance matches this prediction. The concordance between 65-year-old theoretical predictions and modern observations is either remarkable coincidence or genuine confirmation of the theoretical framework. The analysis team assigned statistical confidence to various scenarios. They calculated that natural debris disk explanations have less than 1% probability of producing all observed characteristics simultaneously. Alternative stellar phenomena have less than 0.1% probability. Background contamination scenarios are excluded at 99.9% confidence by spatial analysis and follow-up observations. The technosignature hypothesis, while extraordinary, represents the most statistically likely explanation for the combined set of observations. Though the team acknowledges this doesn't constitute proof and emphasizes the need for additional observations and theoretical work. Alternative explanations. Scientific rigor demands exhaustive examination of conventional explanations before invoking extraordinary scenarios like artificial megastructures. The K218 analysis team and independent researchers have proposed numerous alternatives to the technosignature interpretation, each plausible in isolation but struggling to account for the complete set of observed properties. Understanding why these alternatives fail is as important as understanding what the data show. The debris disk hypothesis represents the most obvious natural explanation. Many stars host circumstellar disks of dust and rocky debris remnants from planetary system formation or material from asteroid collisions and cometary disruptions. These disks absorb stellar radiation and re-emit in infrared, creating excess emission beyond what the star's photosphere alone produces. The solar system contains its own debris structures, the asteroid belt and Kuiper belt, though far too tenuous to produce detectable infrared excess to external observers. For K218, a debris disk explanation requires specific properties. The disk must intercept approximately 18% of stellar luminosity, implying optical depth near 0.2 and substantial mass. It must produce clean blackbody emission at 300 Kelvin without silicate features, suggesting dust composition unlike any observed debris disk. It must maintain azimuthal symmetry and temporal stability over years, unlike typical debris disks that show clumpy structure and variability. Quantitative modeling shows that no realistic debris disk configuration satisfies all these requirements simultaneously. The dust composition problem is particularly acute. Silicate dust, the dominant constituent of observed debris disks, shows characteristic spectral features around 10 and 18 micrometers from CO vibrational transitions. These features appear in every well-studied debris disk from young stars to evolved systems. The K-18 spectrum shows no hint of these features despite having signal-to-noise ratio exceeding 50 across the relevant wavelength range. Invoking unusual dust composition like pure carbon or iron avoids silicate features but introduces other problems. Such materials have different optical properties that make matching the observed spectral shape even more difficult. Another alternative involves planetary atmospheres. Gas giants like Jupiter have thick atmospheres that absorb stellar radiation and re-emit thermally. Could the infrared excess represent thermal emission from a giant planet's atmosphere rather than dust? The energetics immediately challenge this scenario. To produce the observed infrared luminosity requires either an improbably large planet several times Jupiter's diameter or multiple large planets all at similar temperatures. The planet would need mass sufficient to generate substantial internal heat, yet remain at precisely 300 Kelvin despite being only 93 million miles from its star, balancing absorbed stellar flux, internal heat, and radiated cooling. The spatial distribution also contradicts planetary explanations. Planets occupy specific locations in their orbits, moving around the star with periods of months to years depending on orbital distance. The infrared emission should show corresponding orbital motion, appearing offset from the star by varying amounts as the planet orbits. Instead, the emission remains centered on the star to high precision across observations separated by months. This requires either multiple planets arranged symmetrically, an extremely contrived scenario, or emission from a structure that surrounds the star rather than orbits a specific location. Stellar activity provides another potential explanation. Stars generate magnetic fields that produce phenomena including spots, flares, and extended chromospheres that emit at various wavelengths. Could enhanced stellar activity explain the infrared excess? Red dwarfs like K-18's host are known for strong magnetic activity and frequent flares. However, stellar activity typically produces emission at shorter wavelengths, ultraviolet, visible light, and near-infrared rather than the mid-infrared wavelengths where the excess appears. Additionally, activity-related emission shows temporal variability on timescales from hours to months, inconsistent with the observed stability. The accretion disk hypothesis suggests material falling toward the star could generate infrared emission. Young stars often host accretion disks where material spirals inward, releasing gravitational energy as heat and light. However, K-18's host star age of approximately 3 billion years places it well beyond the accretion phase. Accretion disks also produce characteristic spectral signatures from hot gas and dust, including emission lines from hydrogen and forbidden transitions from ionized species. None of these features appear in the K-18 spectrum, ruling out significant accretion activity. Binary companion stars represent another possibility. If K-18 is actually a binary system with a second, cooler star, could that companion produce the infrared excess? Cool stars emit primarily in infrared, so a sufficiently cool companion might explain the observations. However, to produce the observed infrared luminosity requires either a star massive enough to be easily detectable in near-infrared observations which show no companion, nor a very cool brown dwarf at the right temperature. Brown dwarfs show characteristic spectral features from methane and water absorption, absent from the K-18 spectrum. Additionally, binary motion would cause the system's spectral lines to show periodic Doppler shifts, which have not been observed. Gravitational lensing can make background objects appear aligned with foreground stars, potentially creating apparent infrared excess if a dusty background galaxy is lensed into coincidence with K-18. However, gravitational lensing produces specific magnification patterns and typically creates multiple images or arcs. High-resolution imaging shows no evidence of lens structure around K-18. The probability of chance alignment between K218 and a background infrared source bright enough to produce the observed signal is extremely low, less than 1 in 100,000. Based on the surface density of infrared sources at relevant flux levels, interstellar dust along the line of sight between Earth and K218 could absorb stellar visible light and re-emit an infrared, mimicking emission from the star's vicinity. This scenario requires a dense cloud position such that it absorbs visible light from K218 specifically, while leaving nearby stars unaffected. Observations of surrounding stars in the same region of sky show no similar effects, ruling out widespread interstellar extinction. Invoking a small, localized cloud in front of only K218 requires remarkable coincidence. Additionally, interstellar dust shows characteristic spectral features and extinction curves inconsistent with the observations. The collision hypothesis suggests recent catastrophic collision between large planetary bodies could produce debris that temporarily creates infrared excess. The collision between Earth-sized protoplanets that formed Earth's moon generated enormous debris clouds that would have been infrared bright if observed from other star systems. Could K218 have experienced similar recent collision? This scenario makes specific predictions. The debris should be rapidly evolving as material orbits, collides, and accretes. The infrared excess should decrease over timescales of years to decades as debris settles. Follow-up observations show no such evolution. The signal remains constant, suggesting the source is in steady state rather than transient collision debris. Exotic stellar phenomena offer speculative alternatives. Could K218's star have unusual surface properties, perhaps magnetic structures confining hot plasma in specific configurations, or geometric patterns of star spots creating unusual thermal emission? Such scenarios lack theoretical foundation. No known mechanism produces the required geometric patterns and thermal properties. Invoking a known stellar physics to avoid technosignature conclusions substitutes one extraordinary claim for another without improving explanatory power or reducing the need for additional evidence. Multiple object scenarios attempt to explain the observations through combinations of natural phenomena. Perhaps K218 hosts both a debris disk and unusual stellar activity and a background galaxy, with effects combining to mimic technosignature characteristics. While logically possible, such scenarios multiply in probabilities. Each component has low individual probability of producing observed features, and requiring multiple unlikely phenomena to occur simultaneously makes the combined scenario even less probable than single. E-component explanations. The Chem's razor principle favoring explanations that minimize assumptions presents complications in this context. The technosignature hypothesis requires one dramatic assumption: extraterrestrial intelligence exists and builds megastructures. Alternative explanations require multiple assumptions about unusual debris configurations, peculiar dust properties, or unprecedented stellar activity. Which approach truly minimizes assumptions depends on how one weighs the prior probability of extraterrestrial intelligence versus the prior probability of novel natural phenomena. Reasonable scientists disagree on this weighting, leading to different conclusions about which explanation is most parsimonious. Statistical analysis quantifies the relative likelihood of various scenarios. Bayesian methods allow calculating posterior probabilities given observed data and prior expectations. The analysis team performed such calculations, assigning conservative prior probabilities based on known occurrence rates of various phenomena. Even with priors strongly biased toward natural explanations, assigning just 1% prior probability to technosignatures, the posterior probability of the technosignature hypothesis exceeds 50% given the observed data. This doesn't prove the technosignature interpretation but demonstrates that it has become the statistically favored explanation despite its extraordinary nature. Critics argue that absence of known natural explanations doesn't prove artificial origin. It might simply mean we haven't yet thought of the correct natural explanation. This argument has historical precedent. Quasars initially seemed impossibly luminous, potentially requiring exotic physics or even artificial origin. The correct explanation, supermassive black hole accretion, wasn't seriously considered until years after discovery. Could K218 similarly require novel astrophysics not yet conceived? Possibly, but this argument cuts both ways. We must base conclusions on current knowledge rather than hypothetical future discoveries, while remaining open to revising conclusions as new information emerges. Distance implications. K218's distance of 124 light-years places it in our cosmic neighborhood nearby on galactic scales, but still representing a vast gulf that shapes both what we observe and what the detection implies. Light traveling from K218 to Earth takes 124 years, meaning we observe the system as it existed in 1901, during the late Victorian era. If the infrared excess represents a Dyson sphere, we're witnessing a civilization's engineering project from over a century ago by our timeline. Though from their perspective the construction might be ongoing, completed, or even dismantled in the current era that we cannot yet observe. The light travel time creates fundamental limitations on information gathering. Any signal we send to K218 would require 124 years to arrive, and responses would take another 124 years to return to 148 years round trip. This vastly exceeds human lifespans and even the timescale of most civilizations in recorded history. Communication would necessarily span generations, with messages sent by people who will die long before responses arrive, and received by descendants who didn't send the original messages. This temporal disconnection challenges conventional concepts of dialogue and interaction. The distance also affects what we can observe with current technology. JWST's angular resolution at 10 micrometers wavelength is approximately 0.4 arcsecons, corresponding to about 15 million miles at K218's distance, roughly 1/6 of an astronomical unit. This resolution is sufficient to confirm that emission comes from a region surrounding the star, but insufficient to resolve individual components of a hypothetical Dyson swarm. We cannot see whether the structure consists of millions of independent collectors or fewer larger platforms. We cannot detect gaps, geometric patterns, or other structural details that might provide additional evidence of artificial construction. Future telescopes might achieve higher angular resolution through various approaches. Interferometry, combining light from multiple telescopes, can create effective apertures larger than any single mirror. Ground-based infrared interferometers like the Very Large Telescope Interferometer achieve angular resolution around 10 milliseconds, potentially resolving structures down to a few 100,000 miles at K218's distance. Space-based interferometers proposed for future missions could achieve even better resolution, possibly distinguishing individual large components if they exist. The distance places K218 within what astronomers call the solar neighborhood, the region within roughly 500 light-years of Earth where stars can be studied in detail. With current instruments, only about 100,000 stars exist within this volume, a tiny fraction of the galaxy's roughly 200 billion stars. The detection of a Dyson sphere candidate in such a small sample has profound statistical implications. If 1 in 100,000 nearby stars shows evidence of megastructure construction, extrapolating to the galaxy suggests millions of potential megastructures might exist in the Milky Way. This statistical reasoning depends critically on whether K218 represents a typical example or unusual case. Perhaps megastructures cluster in certain regions, stellar types, or galactic environments. K218's host is a red dwarf, the most common type of star, comprising approximately 70% of stars in the galaxy. If red dwarfs are suitable hosts for megastructure construction, the total number of potential sites increases dramatically. Alternatively, if K2-18 is somehow unusual, perhaps located in a particularly metal-rich environment favorable for planetary system formation and subsequent civilization development, the detection might be less representative. The stellar type raises interesting questions about the civilization that might inhabit the system. Red dwarfs have lower luminosity than sun-like stars, meaning planets must orbit closer to maintain habitable temperatures. K2-18b, the super-Earth that prompted the initial observations, orbits at approximately 16 million miles, much closer than Mercury orbits the Sun. At this distance, tidal forces from the star likely lock the planet's rotation, leaving one hemisphere in permanent daylight and the other in permanent darkness. Such conditions challenge conventional habitability concepts, though not necessarily prohibiting life or civilization development. Red dwarfs also live far longer than Sun-like stars, hundreds of billions of years compared to the Sun's 10 billion-year lifespan. A civilization developing around a red dwarf has vastly more time available for technological and cultural evolution. They might also experience different evolutionary pressures. The frequent stellar flares typical of young red dwarfs could drive selection for radiation resistance or underground habitation. The close orbital distances might make space travel between planets easier than in solar system-scale systems. These factors could influence the civilization's trajectory in ways difficult to predict from human experience. The distance affects our ability to detect other technosignatures beyond the infrared excess. If the civilization uses powerful radio transmitters, could we detect those signals? The answer depends on transmission power and frequency. The Arecibo radio telescope, before its collapse, could have detected a transmitter comparable to Earth's strongest radar systems from K2-18's distance, but only if the transmission was directed toward Earth and we observed at the right frequency and time. Searches for radio signals from K2-18 have been conducted but so far show nothing definitive. Either the civilization doesn't use powerful radio transmitters, or their signals aren't directed toward Earth, or we haven't searched the right frequencies. Optical SETI attempts to detect laser pulses that might be used for interstellar communication or other purposes. A civilization using powerful lasers for propulsion, communications, or resource extraction might be detectable across 124 light-years if pulses are bright enough and directed appropriately. Several observatories have conducted optical SETI observations of K2-18, looking for nanosecond pulses that would stand out against the star's steady emission. No detections have been reported, though these searches have covered limited observing time and might miss pulses occurring at times when the system wasn't being observed. The spatial relationship between K2-18 and Earth affects what portion of any megastructure we can observe. Dyson spheres aren't perfectly uniform structures built by civilizations would likely show asymmetries from construction history, resource distribution, or functional requirements. Our viewing angle determines what features we see. If the Dyson swarm has gaps or incomplete regions, whether we can observe those features depends on whether they face toward Earth. The infrared excess might appear different to observers at different locations around K2-18, seeing the structure from varying angles. The galactic context of K2-18 provides additional perspective. The system lies in the direction of the constellation Leo but shares our general galactic neighborhood part of the Orion Spur, a minor spiral arm where the Sun also resides. We're not observing across the galaxy or between different galactic structures. K2-18 orbits the galactic center at roughly the same distance as the Sun, experiencing similar galactic environments including cosmic ray fluxes, supernova rates, and interactions with giant molecular clouds. Any civilization at K2-18 develops under conditions broadly similar to those affecting the solar system. The proper motion of K2-18, its movement across the sky relative to background stars, is measurable and shows the system approaching Earth at approximately 7 miles per second. Over time, K2-18 will grow slightly closer, though the change is negligible over human timescales. In 1 million years, it will be approximately 30 light-years closer, at 94 light-years distance. This slow convergence means that if we could wait long enough, natural orbital dynamics would eventually reduce the distance and improve our ability to study the system in detail. The distance also influences detection probability through selection effects. Closer systems are easier to study, meaning we're more likely to detect technosignatures nearby than far away. The fact that a potential Dyson sphere candidate appeared in a relatively nearby system within the first few years of JWST operations could indicate either remarkable luck or that megastructures are relatively common. If megastructures are rare, say 1 in 10 million stars, detecting one within 124 light-years would be quite improbable. If they're more common, 1 in 10,000 stars detection in the solar neighborhood becomes expected. This reasoning informs estimates of technosignature prevalence based on the K2-18 detection. Statistical methods can calculate the probability of detecting at least one megastructure candidate in a sample of approximately 100,000 nearby stars, given various assumptions about actual megastructure frequency. If megastructures occur on 1 in 100,000 stars, the K2-218 detection is consistent with expected outcomes. If they're rarer, we've been quite fortunate. If they're more common, we should expect additional detections soon as observations continue. The distance prevents us from learning certain information that would be accessible for closer systems. We cannot send probes to K2-218 within relevant timescales, even traveling at 10% light speed far beyond current capabilities. Probes would require over 1,000 years to arrive. We cannot conduct interferometric observations with the angular resolution that would resolve individual components. We cannot detect electromagnetic emissions except the most powerful. We're limited to passive observation using increasingly sophisticated telescopes, analyzing the photons that happen to travel from K2-218 toward Earth. Yet this distance is not prohibitive for meaningful study. We've learned enormous amounts about objects at far greater distances, galaxies billions of light years away, quasars at the edge of the observable universe. Distance constrains but doesn't eliminate scientific investigation. Each technological advance in telescope sensitivity, spectral resolution, or angular resolution reveals new details. The K2-218 system will be observed hundreds or thousands more times over coming decades, with each observation potentially clarifying our understanding of whether the infrared excess represents a genuine megastructure or a natural phenomenon not yet properly characterized. Energy signatures. The energy budget of any detected Dyson sphere provides crucial information about the civilization that constructed it and the structure's purpose. K2-18's host star produces approximately 0.02 solar luminosities, about 5 billion trillion watts, of which approximately 18%, or 900 million trillion watts, appears as thermal infrared excess. This captured energy represents roughly 200 million times humanity's current total energy consumption, suggesting a civilization operating at scales vastly exceeding current human capabilities while still far from complete stellar enclosure. Understanding this energy magnitude requires context. Current human civilization consumes approximately 500 exajoules per year, roughly 5 kW average continuously. This includes all energy sources: fossil fuels, nuclear, renewable, and traditional biomass. The K2-218 infrared excess represents energy capture approximately 200 million times greater. If humanity's energy consumption continues growing at historical rates of roughly 2% per year, reaching K2-18's apparent consumption level would require approximately 1,000 years, distant by human standards, but not by civilizational or cosmic timescales. The partial nature of the detected structure, capturing just 18% rather than complete stellar output, suggests a civilization either still constructing their megastructure or deliberately maintaining partial enclosure for specific reasons. Complete Dyson spheres capturing 95% or more of stellar output represent maximum energy extraction. But partial structures might be preferred for various reasons: maintaining visibility of the star from certain locations, preserving natural illumination for planets, or technical limitations that make complete enclosure difficult or unnecessary. Thermodynamic analysis of the waste heat signature reveals efficiency characteristics. The structure absorbs visible and near-infrared starlight at temperatures around 3800 Kelvin and radiates waste heat at 300 Kelvin. This temperature differential allows extracting useful work through heat engines operating between these reservoirs. The Carnot efficiency, theoretical maximum efficiency for heat engines, is approximately 92% for these temperatures. Actual efficiency will be lower due to practical engineering limitations, perhaps 20 to 40%. This means roughly 1/5 to 2/5 of absorbed energy converts to useful work, with the remainder radiated as waste heat. What might a civilization do with 900 million trillion watts? The possibilities span from mundane to exotic. Industrial processes, manufacturing, mining, material processing scale with available energy. Computation at scales enabling planet-wide or civilization-wide artificial intelligence requires enormous energy, potentially explaining high consumption. Climate control for multiple worlds or artificial habitats could consume substantial power. Advanced particle accelerators or fusion reactors for research might demand continuous high-energy input. or purposes entirely outside human conception might drive energy needs for beings or social structures fundamentally different from human civilization. One intriguing possibility involves computation. Modern computers perform roughly 1,020 floating-point operations per second per watt, a measure of computational efficiency called operations per joule. With 900 million trillion watts, a civilization could theoretically perform roughly 1,038 operations per second, far exceeding all computation ever performed by humanity. Such computational resources might enable simulating entire planetary ecosystems in real time, running millions of ancestor simulations, or computing solutions to problems requiring vast state space exploration. If civilizations universally trend toward computational focus as they advance, energy consumption might be dominated by computing rather than physical industry. The energy signature also constrains what the civilization is not doing. They're not engaging in stellar lifting, extracting material directly from the star's outer layers, which would show characteristic spectral changes not observed in K218 spectrum. They're not using antimatter in large quantities. Antimatter annihilation produces characteristic gamma-ray signatures not detected. They're not conducting large-scale relativistic particle acceleration, which would create observable radio emission from synchrotron radiation. The absence of these signatures doesn't mean the technologies don't exist, but they're not dominating the energy budget. The waste heat temperature of 300 Kelvin has specific implications. This temperature is comfortable for organic life, roughly room temperature by human standards, suggesting either biological inhabitants or technology designed to operate at temperatures compatible with biological components. Higher operating temperatures would increase thermodynamic efficiency but make maintaining biological habitats more difficult. Lower temperatures would decrease efficiency and require larger radiating surfaces. The observed temperature might represent optimization between engineering efficiency and biological requirements. Alternatively, the 300 Kelvin temperature might be purely engineering-driven, unrelated to biology. Thermal management for large-scale structures requires radiating heat efficiently while maintaining structural integrity. Many materials have favorable properties around room temperature: ductile metals, stable polymers, practical superconductors. Solid-state electronics typically operate best below approximately 350 Kelvin. The observed temperature might simply reflect engineering sweet spots rather than biological constraints. The spatial distribution of energy generation provides clues about structure architecture. Is energy collected uniformly around the star or concentrated in specific regions? JWST's limited angular resolution cannot distinguish between these possibilities, but future high-resolution observations might detect asymmetries. Uniform distribution suggests a mature, completed structure designed for maximum efficiency. Concentrated regions might indicate ongoing construction, with completed sections operational while others remain unbuilt. Or functional requirements might concentrate collectors in specific orbits, perhaps at latitudes aligned with planetary systems, or avoiding regions with high meteoroid flux. The time stability of the energy signature over 2 years of observation indicates a system in steady-state operation rather than experiencing rapid changes. The infrared luminosity varies by less than 3% within measurement uncertainty, suggesting either extremely stable energy capture or time averaging over fluctuations, occurring on shorter time scales than observational cadence. Rapid construction or dismantling would show systematic trends in infrared output as more structures came online or were removed. The stability suggests the megastructure is either complete or changing slowly enough that year-to-year variations are negligible. Comparison with theoretical predictions for different civilization types provides context. The Kardashev scale classifies civilizations by energy consumption. Type 1 harnesses roughly kW planetary scale, Type 2 harnesses roughly kW stellar scale, and Type 3 harnesses roughly kC galactic scale. K218 civilization, if real, operates at approximately kW, approaching Type 2 but not yet there. This places them at a transitional stage where planetary energy sources no longer suffice, but complete stellar enclosure hasn't been achieved. This stage might be relatively brief in civilizational development, making detection of civilizations at precisely this point somewhat fortuitous. The energy signature also enables calculating approximate timescales for construction. If the structure has mass comparable to Earth, roughly 1,025 kilograms, and construction requires energy to extract, process, and position materials, the total energy investment might be 1,032 kJ. At captured power of 1,024 watts, accumulating this energy requires roughly 108 to 109 seconds, approximately 3 to 30 years. This assumes all captured energy goes toward construction and realistic for any functioning civilization. With 10% dedicated to construction, timescales extend to 30 to 300 years. These estimates are highly uncertain but suggest construction timescales of centuries, rapid by geological standards, significant by human civilizational standards. The missing energy, the approximately 82% of stellar luminosity not captured by hypothetical structures, continues radiating into space. Observers at other locations around K218 would see this in captured starlight, potentially observing the system as an apparently normal red dwarf without obvious anomalies. Only observers at locations where absorbed light creates shadows, where structures block direct starlight, would detect infrared excess without seeing corresponding visible light. This geometric effect means that not all observers would recognize K218 as hosting a megastructure, highlighting the importance of observing angle and technosignature detection. The energy analysis raises philosophical questions about civilization development. Is high energy consumption inevitable for sufficiently advanced civilizations, or might some societies stabilize at lower consumption through different development paths? Does intelligence inherently lead to expansion and increased resource utilization, or might some civilizations deliberately limit growth? The K218 detection, if confirmed, would suggest at least some civilizations follow expansionary trajectories requiring ever-increasing energy, providing one data point in understanding whether this represents convergent evolution of intelligence or merely one possible path among many. Scientific controversy. The K218 detection has divided the astronomical community into roughly three camps: those convinced the observations represent genuine technosignatures, those convinced natural explanations must exist despite current inability to identify them, and those maintaining skeptical neutrality while awaiting additional evidence. This division reflects both the extraordinary nature of the claims and legitimate philosophical differences about how to interpret ambiguous data when dealing with unprecedented phenomena. The strongest skeptics argue that invoking extraterrestrial civilizations represents premature abandonment of natural explanations. They point to historical examples where seemingly inexplicable observations eventually received conventional interpretations. Quasars, when first discovered in the 1960s, seemed impossibly luminous, so energetic that some scientists briefly considered artificial origins. The correct explanation, supermassive black holes accreting matter, wasn't broadly accepted until years of additional observations and theoretical development. Pulsars were briefly designated LGM for little green men before being identified as rotating neutron stars. These skeptics contend that absence of known natural explanations doesn't prove artificial origin. It might simply mean we haven't yet conceived the correct natural explanation. The universe has repeatedly surprised us with phenomena not predicted by theory. Perhaps K218 involves some combination of unusual circumstances, specific dust composition, peculiar stellar activity, or geometric coincidences that mimic technosignature characteristics. Declaring the detection artificial risks embarrassment if subsequent observations reveal mundane explanations. Proponents counter that science must draw conclusions based on current knowledge rather than hypothetical future discoveries. They argue that extraordinary claims require extraordinary evidence. But the converse also holds. Dismissing data that doesn't fit conventional explanations requires evidence that alternative explanati odds exist. If every conventional hypothesis has been tested and failed, continuing to insist on natural explanations without specifying what those might be represents wishful thinking rather than scientific skepticism. The philosophical debate extends to questions about prior probability. Bayesian reasoning requires assigning prior probabilities to different hypotheses before examining evidence. What prior probability should we assign to extraterrestrial civilizations existing and building megastructures? Skeptics argue this probability is extremely low, perhaps 1 in millions or billions, making technosignature explanations inherently disfavored regardless of data. Proponents argue the prior probability is unknown and might be substantial, making technosignatures no more extraordinary than many other astronomical phenomena. The controversy also involves disagreement about burden of proof. Skeptics claim proponents must definitively prove artificial origin, ruling out every conceivable natural explanation before the technosignature hypothesis becomes acceptable. Proponents argue that having tested all known natural hypotheses and found them wanting shifts burden of proof to skeptics, who must propose specific testable alternatives rather than simply asserting that a known natural phenomena must exist. Both positions have merit, leading to different conclusions about whether current evidence suffices. Sociological factors influence the debate beyond pure scientific reasoning. Claiming detection of alien intelligence carries career risks. Researchers might be dismissed as sensationalist or unrigorous if the detection proves mistaken. Institutional cultures in astronomy generally favor conservative interpretations of ambiguous data. The field of SETI has struggled for funding and respect despite decades of effort, making researchers wary of overconfident claims that might further damage credibility. These pressures influence how scientists publicly discuss the K218 detection regardless of their private assessments. The controversy has generated sharp exchanges in scientific literature. A paper by Rodriguez et al. 2025 argued that the K218 team failed to adequately consider warm dust scenarios and that specific dust compositions could reproduce the observations without invoking artificial structures. The original team responded with detailed analysis showing why proposed dust models failed to match all observational constraints simultaneously. This exchange typifies scientific debate at its best: specific, technical, and focused on quantitative analysis rather than rhetoric. Other researchers have proposed observational tests to distinguish between natural and artificial interpretations. Dr. James Nakamura at Caltech suggested that monitoring the system over decades might reveal evolutionary trends. Natural phenomena evolve on astrophysical timescales, while artificial structures might show deliberate modifications. Dr. Elena Volkov at the Max Planck Institute proposed high-resolution spectroscopy searching for specific molecular signatures that would definitively indicate either circumstellar chemistry or industrial processes. The controversy highlights differences in how scientists weigh different types of evidence. Some emphasize the quantitative match between observations and Dyson sphere predictions, viewing the concordance as powerful evidence for artificial origin. Others emphasize the lack of definitive smoking gun that would exclude all natural alternatives, viewing the case as suggestive but not conclusive. Both approaches are scientifically legitimate, leading to different assessments of whether the detection represents probable, possible, or unlikely technosignature. Media coverage has influenced the scientific debate in complex ways. Popular science reporting often presents the discovery as confirmed detection of alien megastructures, overstating confidence levels and ignoring caveats emphasized by researchers. This creates public expectations and pressures that affect how scientists discuss the work. Some researchers have retreated from strong claims to avoid appearing to feed media sensationalism. Others have leaned into public engagement, arguing that extraordinary possibilities deserve public discussion even amid scientific uncertainty. The controversy has sparked renewed interest in developing frameworks for technosignature evaluation. The real scale, proposed in the 1990s for rating potential SETI detections, provides one such framework. The scale combines assessment of signal credibility with potential consequences of contact, yielding overall risk assessment. Applied to K218, different researchers rate the detection anywhere from 4 to 7 on the 0 to 10 scale, substantial disagreement reflecting the controversy. Work continues on refining such frameworks to provide more objective methods for evaluating ambiguous detections. International scientific organizations have begun developing protocols for handling potential technosignature detections. The International Academy of Astronautics maintains a post-detection protocol outlining steps for verification, announcement, and information dissemination. However, these protocols were developed primarily for radio SETI and don't perfectly fit infrared megastructure detections. The K2218 case has prompted discussion about updating protocols to cover diverse technosignature types and different levels of detection confidence. The controversy also raises questions about publication standards. Should journals apply different evidentiary standards to claims about extraterrestrial intelligence versus other astronomical phenomena? Some argue that extraordinary claims require extraordinary peer review, with higher bars for publication than normal research. Others contend that this double standard and fairly disadvantaged technosignature research, and that all claims should face equally rigorous review regardless of implications. Funding implications add practical dimensions to the controversy. If K2218 represents genuine technosignature detection, substantial resources should be devoted to follow-up observations and confirming the finding. If it represents misidentified natural phenomena, those resources would be wasted. Funding agencies must decide whether to support extensive follow-up programs without conclusive evidence the detection is real. The controversy creates a chicken and egg problem. Confirming the detection requires resources, but securing resources requires evidence the detection deserves confirmation. Personal relationships and prior positions influence the debate. Researchers who have spent careers arguing that technosignatures are indetectable with current technology face cognitive dissonance if K2218 represents genuine detection. Those who have advocated for infrared SETI feel vindicated and perhaps overconfident. Scientists who dismiss the possibility of nearby megastructures resist evidence threatening their previous conclusions. These human factors don't invalidate scientific arguments but affect how arguments are presented and received. The controversy has generated productive outcomes regardless of ultimate resolution. New theoretical work has refined predictions for Dyson Sphere observables, enabling better designed searches. Observational techniques have improved as researchers develop methods to distinguish technosignatures from natural phenomena. The field of technosignature science has gained legitimacy and funding, enabling studies that benefit multiple areas of astronomy. Whether or not K2218 proves artificial, the debate has advanced scientific understanding. Historical perspective suggests the controversy might persist for years or decades before resolution. Major astronomical discoveries often face extended skepticism before acceptance. Black holes were theoretically predicted in 1916, but not broadly accepted until the 1970s after observational evidence accumulated. Exoplanets were suspected for centuries but not confirmed until the 1990s, with early claims facing intense skepticism. If K2218 follows this pattern, definitive resolution might require technological advances not yet available, while the debate continues based on currently available evidence. The controversy ultimately reflects healthy scientific process. Extraordinary claims face intense scrutiny. Multiple researchers independently test conclusions. Alternative explanations are rigorously evaluated, and consensus emerges gradually as evidence accumulates. This process produces reliable knowledge precisely because it resists premature conclusions and demands high evidentiary standards. Whether future research confirms or refutes the technosignature interpretation, the careful analysis and vigorous debate surrounding K2218 exemplify science functioning as intended.